What in the name of science is this? Oh my, science!
Hey everybody, welcome to Oh My Science. I'm Sean Murray, and today I'm going to be talking about scanning electron microscopes and how they're used to produce those high magnification images that you see in all the scientific publications. We are going to learn about this instrument by looking at a piece of rock from outer space. That's right, I actually got my hands on a genuine piece of meteorite here from our collection at Macquarie University. I'm not quite sure which meteorite it is, but I was told that quite a few people got injured trying to acquire this specimen. All right, it might be a bit dramatic, but you kind of get the idea. Just looking at this thing by hand, you can see it here, nice little thin section. You can't really see much. It's brownish, there's a couple specks of orange and gray in there, but can't really make out too much. So, of course, the first thing you should ever do whenever you get a thin section just like this, stick it under a petrographic microscope. So here you can see what the meteorite looks like at 2x magnification. I took a map of the whole slide and stitched together the individual images to produce what you are seeing here. Compared to just looking at the thin section by eye, a few more things start to jump out. The colors are more dramatic, you can start to see some of the grain shapes and some different textures in there, but we're still missing some of the finer details. So of course the next thing to do is to increase the magnification. So here I've bumped things up to 10x magnification. And now we can begin to see some of these really interesting details. There are a couple circular regions with unique textures, some grains that are an amalgamation of multiple minerals. You can really see that melted molten material starting to coalesce into this solid asteroid body. Now I tried to go further than this, pushing the microscope to 20 or even 50x magnification, but I struggled to get a clear image. It just kind of looked like a black blob to me. So instead, I took the thin section and went directly to the Scanning Electron Microscope, or SEM for short. So I managed to locate the exact same location in both the petrographic microscope image at 10x magnification and the SEM image at 50x magnification, which is kind of about the starting point for the SEM. Looking at the SEM, a few details pop out which could not be seen in the petrographic microscope image, including these two circular grains on the left-hand side. Now, of course, the most obvious thing to comment on is the lacking of color in the SEM image. But what the image lacks in color, it makes up for in magnification power. Now, you can't see this in the image here, but right here, in the center of this bullseye, there are 3 really bright grains. So let's zoom in here. This is now at 5,000x magnification. And you can see we have a nice, crisp image showing these 3 bright grains within the darker matrix. Now, SEMs can be pushed further, maxing out at about 100,000 to 300,000 times magnification, while still maintaining a high resolution, which basically means just that the image still looks good. So the question is, how does an SEM produce such images? Here we have a comparison of a light microscope and an SEM. In a light microscope, you have a light source that shines either on top of or through your sample. The light is then focused through a series of lenses before hitting your eye. An SEM works very similarly. Instead of a light source, there's a filament, similar to that of a light bulb, called a cathode. By passing an electrical current through the filament, it heats up and begins to emit electrons. To increase the mobility of the electrons, all of this is done under a very high vacuum, similar to the conditions in outer space. Since we are dealing with electrons which have a negative charge, we use electromagnets instead of lenses to drive and focus the electrons into a beam that hits the sample. The electron beam rapidly scans across the surface of the sample in rows, kind of like an old-fashioned printer. At each point, a number of electrons will bounce back from the sample, which are then picked up by an electron detector hooked up to a computer. The detector interprets the signals from the electrons and produces an image. While SEM images might not have color, they do have an increased depth of field, which gives SEM images a very lifelike appearance, which makes them very attractive in scientific articles. This is possible because the varying shades of gray in the image are based on how many electrons bounce off a point and reach the detector. A point where the electrons bounce away from the detector instead of towards it will produce a darker point in the final image. So that's all I've got for today. I hope you learned a bit about how an SEM works. If you have any questions, just look out for your Oh My Science guy here at Macquarie University. Take care, everyone.